Let us continue Carnot cycle. We are continuing Carnot cycle. In the Carnot cycle, 4 steps are there. First step we will take. First step is isothermal, reversible, expansion of ideal gas. Expansion of ideal gas. This is a expansion isothermal in the sense temperature remains constant. Expansion of ideal gas, so it obeys which law in the sense Boyle's law. So Boyle's law graph we will draw. Here we will take pressure, here we will take volume. So we are getting a graph like this. Okay. So it is the initial state we will take, the initial pressure, initial volume we will take. It is the final state, final pressure, final volume we will take. Temperature remains constant in this process, that we will take it as T2. Okay. Now, in this process, expansion in the sense system has to do work. That means gas has to do work. Now we will see work done by the ideal gas. That work done symbol we will take, W2 we will take, which is equal to minus nRT ln final volume by initial volume. In this process, delta U we can say 0, delta H we can say 0. First law of thermodynamics mathematical form, delta U is equal to Q plus W. Delta U will substitute, therefore Q is equal to minus W. So system is doing work by absorbing heat from surrounding, because internal energy is not changing. Okay, therefore heat absorbed by the system, heat absorbed by the ideal gas, that symbol will take U2 is equal to this W2 will take it is. W2 is how much? nRT ln V2 by V1. W2 is equal to minus nRT. Q2 is equal to plus nRT, because Q is equal to minus W. So next step we will see. We are going for second step. Adiabatic reversible expansion of ideal gas. So we are seeing what in the sense adiabatic reversible expansion of ideal gas we are seeing. Okay. For this adiabatic process in the sense Q is equal to 0. Adiabatic process in the sense Q is equal to 0. We will substitute this Q value in first law of thermodynamics mathematical form. Here delta U is equal to Q plus W. Substitute Q, what you will get? Delta U is equal to W you will get. Okay. Sir, for this here system is doing work. For doing work, system is not absorbing any heat from surrounding because it is adiabatic. In the previous case, this ideal gas is doing expansion. Ideal gas is undergoing expansion. Ideal gas is doing work for which it has absorbed heat from surrounding. How much work it has done, that much amount of heat it has absorbed from surrounding. Therefore, internal energy remains constant. But in this case, in this adiabatic process, ideal gas is doing expansion, but it is not taking any heat from surrounding. Therefore, it utilizes its own energy. Therefore, its internal energy decreases. Internal energy decreases in the sense kinetic energy decreases. Kinetic energy decreases means temperature decreases. Okay, so temperature of this ideal gas decreases in this place. Okay, now so delta U is equal to what formula means? NCVM delta T. Delta T means final temperature minus initial temperature. Final temperature we will take it as T1. Initial temperature is T2, already mentioned. Here in this place, this place is called initial temperature. This place temperature is how much means T2 is mentioned. That T2 we have taken. Initial temperature is T2. Final temperature is T1. Like this we have taken. Okay. Now, for this we will draw the graph. For this we are drawing the graph. The graph comes like this. The graph comes like this. Here, temperature for this it is attaining temperature how much, in the sense T1. Here starting point, it is the starting point. Here temperature is T2, but when the process goes on like this, temperature goes on reducing, decreasing, and attains T1 here. Here pressure is P3, volume is V3. Like this we can take. It is the second step. In this second step is a adiabatic reversible expansion of ideal gas, we can say. Second step is adiabatic reversible expansion of ideal gas. Okay. So here Q is equal to how much, in the sense 0. Delta U is equal to W. Now it is a NCVM delta T. Delta T is final temperature minus initial temperature. Final temperature is T1. Initial temperature is T2. In this process, temperature decreases. Okay. Next step. Now we will go for third step. Third step is isothermal reversible compression of ideal gas. Okay. Isothermal reversible compression of ideal gas, we'll see. Okay. Here isothermal, in the sense temperature remains constant. Now work done, here system is doing work or external is doing work, in the sense system is undergoing compression, ideal gas is undergoing compression. Compression in the sense somebody has to compress it. Therefore, external is compressing this ideal gas. So external is compressing ideal gas, in the sense we can say work done on the system, work done on the ideal gas. Okay, this work done symbol will take W1. Here work done is minus nRT ln final volume by initial volume. Final volume we will take it as V4. Initial volume we will take it as V3. Okay, for this final volume is here initial volume. Okay, so here volume is how much, V3, that is initial for this compression. Okay, final volume is V4. Okay, then delta U is equal to 0 because isothermal, delta H is equal to 0. Then system is work is done on the system, in the sense it receives it will release heat. Why it has to release heat? External is doing work, therefore it is getting energy, but internal energy should remain same. Why? Because isothermal. Then it is getting energy, in the sense it has to leave that energy, no, therefore it liberates heat. Okay, heat released by the system, heat released by the gas, heat released by the gas is equal to Q1 symbol will take, that is equal to nRT ln V4 by V3. Okay, Q sign and W sign will be opposite for isothermal because delta U is equal to 0. Okay, so for this we will draw the graph. Okay, isothermal reversible compression of ideal gas. For that how the graph will be there, we will see. The graph will be like this. Sir, here temperature remains constant in this process, that is T1. Here what is the temperature T1? That temperature remains constant here. Okay, then pressure, final pressure is P4, initial final volume is V4. Like this we can say. Next step adiabatic reversible compression of ideal gas. Adiabatic reversible compression of ideal gas, that we will take. Here we know that Q is equal to 0. Therefore, delta U is equal to W. W is equal to NCVM. Delta T we have to say. Okay. Here compression, in the sense external is doing work on this. Therefore, this ideal gas is receiving work. Receiving work, in the sense what will happen? Its internal energy will rise because Q is equal to 0. It cannot release heat to the surrounding. This ideal gas should not release heat to the surrounding. Okay, but it receives work. External is doing work on it. It receives work. It is receiving work, in the sense it receives energy. It is receiving energy, in the sense what will happen? Its internal energy will rise. That means its kinetic energy rises. Kinetic energy rises means temperature rises. So temperature rising to T2. So final temperature is T2, initial temperature is T1. Okay. Therefore, for this we will draw the graph. So for this we are drawing the graph. It comes like this. The cycle is completing now. Okay. So here temperature is T1 here, that becomes T2. Temperature becomes T2, we can say. T1 temperature becomes T2 temperature. Like that we are saying. Okay. Here final pressure is how much in the sense P1, final volume is V1. Okay. So these are the 4 cycles here. Okay. Now we will see. Now we have completed the cycle. This cycle is called Carnot cycle. What is the work done in this cycle? That we will see. Okay, now we will see total work done in the cycle. So total work done by the cycle we will see, that is equal to first step work done. First step is called what? Isothermal reversible expansion of ideal gas. That work done symbol is W2. Second step, adiabatic reversible expansion of ideal gas. That work done is W symbol. W symbol. Then third step, isothermal reversible compression of ideal gas. That work done is W1 symbol. Fourth step, adiabatic reversible compression of ideal gas. That symbol, work done symbol W dash we will take. So that W dash we will substitute. Okay. So work done we have written. Now we will substitute the values. We will substitute. First W2. W2 value will substitute minus NR T2 ln V2 by V1. Okay. W2 work done will take. This first step work done minus nRT ln V2 by V1. T is the temperature. Temperature is how much in the first step? That is T2. First step temperature is T2. Therefore, we will substitute T2 here. Okay. Sir. So first step work done is minus nRT2 ln V2 by V1 plus W. W is called second step work. Second step work, how much we got? That we will see. Second step work is this much. NCVM T1 minus T2, that we will write. Okay. Second step work, NCVM into T1 minus T2. Third step work. Third step work we will see. In the third step minus nRT ln V4 by V3. Third step in the sense isothermal reversible compression of ideal gas. In this place, it is a third step. Third step temperature remains constant. That is how much in the sense T1. So that T1 will substitute. So third step work we will take. Third step work is how much in the sense minus NR T1 ln final volume is V4, initial volume is V3, that we have taken. Okay. Next, fourth step work we will take. Fourth step work is how much in the sense NCVM into T2 minus T1. So we have taken like this. Now you see that can we cancel anything? You see here NCVM T1 minus T2, but here NCVM T2 minus T1 is there. Now we can cancel these two. How in the sense, suppose if you write this is T1 minus T2, then it will become negative minus sign. Therefore, this and this get cancelled. So what is the remaining in the sense here? NR T2 ln V2 by V1. This we can write it as NR T1 ln V4 by V3. Okay, we have written like this. So what is the common terms? It is sorry. Okay, this is called what in the sense total work done. Okay, sorry. So now we got a total work done. We have seen. Now we will see total work done graphically. We will see. It is the total work done we got. Okay, total work done we got. Now we will see graphically. Sir. Now graphically how the total work done will be that we want to see. Okay, we will draw the graph. Here we will take pressure. Here we will take volume. First step is called isothermal reversible expansion of ideal gas. That is first step. It is the first step. First step work done we will give. First step work done in the sense area under the curve is called first step work done. This is the first step work. So first step work we have mentioned here. Area under the curve is called first step work. That is isothermal reversible expansion of ideal gas. That work we have given here. Okay, first step work we have given. Next we will go for second step. Second step is what in the sense isothermal, adiabatic reversible expansion of ideal gas. That is second step. Second step is like this. That second step work done we will give. Second step work done we will give. Okay. So we are giving a second step work done. This is what in the sense a second step work done. Okay. Here expansion in the sense work done by the ideal gas, work done by the system, work done by the system. Okay. So first step is work done by the system. Second step also work done by the system. Sir, now work done by the system means useful or not useful. Work done on the system, useful or not useful, that you say. Okay, work done by the system, work done on the system, which is useful, which is not useful generally, which is useful, which is not useful generally, that we will see. Okay, for that case we will take a automobile, we will take automobile engine, we will take. In the automobile engine, how it will be there means it is like a piston manner, it will be there, it is like a piston manner, it will be there. Okay. In this what comes in the sense, petrol comes, petrol, and air comes. Okay, we are kicking this one in the sense it is, we are igniting this one, therefore petrol is burning with oxygen. Okay, petrol in the sense hydrocarbon CXHY. Petrol in the sense hydrocarbon, it contains carbon atoms and hydrogen atoms. Carbon takes oxygen and gives carbon dioxide, hydrogen takes oxygen and gives water, and some other substances plus heat. Because it is burning, petrol is burning, therefore heat is produced. Heat is produced in the sense, what will happen here, gases will undergo expansion here in this engine, in the sense it is just like a piston arrangement, that's all, that nothing more. Piston arrangement. Here petrol liquid is coming, air is coming into this place, then we are igniting this one, we are igniting this one means we are starting the vehicle. We are starting the vehicle in the sense petrol is burning with air. Petrol is burning means petrol contains carbon, that carbon is converting into carbon dioxide. Petrol contains hydrogen, that is converting into water. It is in gaseous state, it is also in gaseous state, and lot of heat is produced. Lot of heat is produced means these gases will be at high temperature and they will undergo expansion. Expansion in the sense piston will be pushed up. Piston is pushed up in the sense vehicle is moving. Once a piston is moving up in the sense, automatically piston will come down, then only cyclic process. Okay, so automatically piston is coming down in the sense, when piston is coming down, the gases will be coming out through exhaust, coming out through exhaust. Okay, now you say that piston is moving up. Now piston is moving up in the sense, piston is moving up in the sense vehicle is moving, vehicle is moving, we can say. Okay, piston is coming down in the sense exhaust gases coming out, exhaust gases coming out. Therefore which is useful work, which is not useful work, you think? So the piston is moving up because of these gases are undergoing expansion, isn't it? So system is doing work, work done by the engine, work done by the engine in the sense vehicle is moving front. This piston is coming down because piston has to move up and down. Okay, piston is moved up because of expansion, piston is coming down, automatically it will come down while exhaust gases go out. So exhaust gases go out because of compression. Piston is coming down, no compression. Now you say which is useful work, which is not useful work, you say. This expansion in the sense work done by the system, compression in the sense work done on the system, which is useful work, which is not useful work. This we can say useful work, we can say it is not useful work, because exhaust in the sense it is going out. Exhaust gases, if you see, it is hot or not, it is also at a high temperature, no? We are making the petrol to burn, and we are getting heat energy in order to make the vehicle to go. But in exhaust gases in the sense it is at high temperature, it is at high temperature, it is going outside in the sense heat energy is lost. Heat energy is lost in the sense it is not useful work, no, it is not useful work. This compression is not useful work, expansion is the useful work. Therefore work done by the system, expansion means work done by the system, useful work. Compression means work done on the system, it is not useful work. Okay, sir, which is useful work, which is not useful work, we got an idea. Step 1 is called expansion. Therefore, work done by the system. Work done by the system is how much means area under the curve. This work is called useful work. Number 2 is also expansion. Area under this curve is called work done. This work done also useful work. Okay. Next, we will go for third step. Third step is called what in the sense? Isothermal compression of ideal gas. That graph we will see. We are seeing third step graph. Third step graph we are seeing. It is third step graph. Third step graph work done we will see. Third step graph work done we will see. Third step means compression. Third step work done in the sense area under the third step curve. Area under the third step curve is called work done. Okay, that work done we'll see. Area under the third step work, that is called compression work. So third step work we are mentioning now. Third step work we are mentioning here. Okay, third step work we have mentioned. Third step in the sense compression, that work is not useful. Okay. First step in the sense, first step work done is how much? From year to year. That is first step work done. Second step work done in the sense from year to year. That means area under this curve to this horizontal line. Because of this third step, this much work done. This much work done is cancelled, or what you see? Now, this much work by first step and second step is cancelled due to third step, isn't it? Now see, now I will show that some area. This area you see that. Now I am pointing out some area. This area of work of first step and second step is cancelled by third step, isn't it? That means though first step is giving useful work, second step is giving useful work, because of this third step, that first step work is something is cancelling out, second step work also something is cancelling out. Okay, network only we have to see. No, why we have to see network in the sense, suppose we are taking 1 liter petrol, it is burning to give x kilojoule of heat. In this x kilojoule of heat, some amount is used for a expansion, that is y kilojoule. Some amount is compression, that is z kilojoule. X is equal to y plus z. Now what happens? X is we are giving in the form of petrol. Y is useful. Y is useful. Actually, X is useful only. In that useful, something is wasted. Something is wasted. Z is wasted. Correct? So that first step work and second step work, some amount is cancelled by third step. Okay, then we will see fourth step. Now, fourth step is compression. Fourth step is compression. That fourth step work we will write. It is fourth step. This fourth step is compression in the sense this work is not useful. That fourth step work I will mention here. Fourth step work I am mentioning. Okay, fourth step work. Now see, first step work is how much in the sense area under the first step curve. This is first step work. First step work means this curve under that to the horizontal line up to that first step work. In that some work is cancelled by fourth step. That is fourth step work is how much means area under fourth step curve. Area under fourth step curve is, this is fourth step curve. This area under this area. This is fourth step work. Due to this fourth step, some amount of work of first step is cancelled out. That means becoming waste. Due to this fourth step, some amount of work of first step is cancelled out. Sir, that means what is the net work done? What is the net work done in the sense this enclosed area? Enclosed area in the sense this point A, this point B, this point C, this point D, this ABCD, enclosed area of ABCD is called useful work. Useful work, that is the net work done. Enclosed area is what? ABCD. Enclosed area is called ABCD. That is only net work done by the system. Net work done by the system. Okay, so net work done by the system, in the sense what we can say, in the sense area of ABCD, we can say area of ABCD is called net work done. So what is a net work done? We'll see now. Now it is a first step curve, second step curve, third step curve, next fourth step curve. Now what is the network done? Means this is the network done. Okay, it is the network done. Area enclosed area is called network done. Okay, sir. So now we have seen network done. We have seen. Now shall we say network done is by the system, on the system? What do you say? Now network done we got. Network done, shall we say by the system, shall we say, or on the system, shall we say? That is this net enclosed area, in the sense 1 and 2 work only. Enclosed area in the sense 1 and 2 work only, 3 and 4 not. 3 and 4 not. Therefore 1 and 2 work in the sense by the system. Therefore net work done by the ideal gas, we can say. So net work done by the system in the sense useful work. Network done by the system in the sense useful work, we can say. Okay, next we will do, this is V2 and V1, this is V4 V3. Let us change this V4 and V3 in terms of V2 and V1. Then calculating network done is easy. Otherwise here how many variables? See, V2, V1, V4, V3, like this variables are there. We will make it as only 2 variables, V1, V2, like this we will make. We are making V4 and V3 as V2 and V1, V1 we will make it. Okay, then calculation will be easy. Okay, then T1, T2 we cannot do anything. T1, T2 will be as it is, will be there. Okay, so this alone we will change this V4, V3 by V2, V1. How to do that? That we will see. Okay, sir. Now we will see second step we will take now. Now we are taking second step. The second step is what? In the sense adiabatic reversible expansion of ideal gas. Okay, this second step we will take. In the second step, delta U is equal to W. The second step is delta U is equal to W. That point we will take. Okay, delta U is equal to W. Now we are taking second step. Delta U is equal to W. It is reversible. In the reversible, first step I will take. First step in the sense du is equal to dw, we can say. Du is equal to dw, because reversible in the sense infinite number of steps. In each step infinitesimal work. Okay, therefore du is equal to dw, we have written. Sir, now we will write du is equal to what? In the sense n cvm dt. N cvm dt. dw is what? In the sense minus pressure of gas dv. Minus pressure of gas. For reversible process alone we have to say pressure of gas. If it is irreversible, here we have to say external pressure, we have to say. Okay, sir. Next step we will see. Next step we will substitute. So n cvm dt, we will make it as a dt we will make it as what? Dt we will write it, and pressure of gas we will write it as minus nRT by V, nRT by V dV. Okay, now for entire process we will see. For entire process how it will be there, we will see. So n cvm dt, here T1 T2 equal to this, we will write minus nR. For second step, what is the temperature? T1. For second step, initial temperature is how much? Means T1. Final temperature how much? Means T2, isn't it? Okay, that's why we have written T1 T2. Okay, so this T we will take, we will bring this side. This T we will bring this side, because temperature is changing, so we will bring this side. So here what will be there? Means minus nR only will be there, and dV by V will be there. Okay, In here, volume change we will take. What is the initial volume for second step? V2. What is the final volume? V3. Sorry, for second step, what is the initial temperature and final temperature? For second step, initial temperature is T2, final temperature is T1. Okay, for second step, initial temperature T2, final temperature T1, initial volume V2, final volume V3. Okay, sir, like this we have written for second step. Now we will take fourth step. We will take for fourth step also we will write same du is equal to dw. We can write because adiabatic. So du in the sense ncvm dt we will write, dw in the sense minus pressure of gas dv we will write. Then next step we will write pressure of gas in the sense minus nRT by v dv we will write. This t we will take this side. So ncvm dt by t, this t right side t we are bringing left side, then minus nr dv by v. Okay, now we will take integration because we want for entire process, because it is for single step. Now entire process in the sense here initial temperature is T1, final temperature is T2, initial volume is V4, final volume is V1. Okay, sir, we have written like this. Next, what I will do here in the sense, I will change something here. What is the change? You see, NCVM. Here what I will do means T2 to T1 I will write. If I write like this, then it will become plus. Okay, NR integration V4 V1 dV by V. Okay, so what I have changed? See, I have changed the limits. I have changed the position of limits. T1 I have taken up, T2 I have taken down, while this negative sign becomes positive sign. Okay, that means here minus will come, that minus cancels, therefore like this. Now you see left side here, you see left side here, remain same or different. You see here left side remain same. Okay, now substitute this here. So you are substituting, therefore what we will get here, what we will get, we will say, otherwise substitute this one here. So minus nr integration V2 V3 dV by V is equal to nr integration V4 V1 dV by V. Okay, now we will integrate it. So here minus nr, this on integration we will get ln V we will get then final and initial. Okay, final limit by initial limit. Here nr ln V, this on integration will get ln V, then final limit by initial limit. Okay, that means this upper limit we have written, this lower limit we have written here. Okay, then next step we will see. Next step what we are doing, see, this minus I will make it as plus by interchanging this. Therefore it will become nr ln V2 by V3. Okay, see that this V3 by V2 we are writing as V2 by V3, while minus becomes plus. Then is equal to what we can say means nr ln V1 by V4. Okay, we have written like this. Next, what is getting cancelled in the sense nr is getting cancelled. Okay, nr is getting cancelled. So what is there means ln V2 by V3 is equal to ln V1 by V4. Then cancel ln also. Therefore, what is that means V2 by V3 is equal to V1 by V4. Okay, V1 by V4 we got. Now what we want means V4 by V3 we want. Therefore, V4 by V3 is equal to what in the sense V1 by V2. Okay, V4 by V3 is equal to what? V1 by V2. Now we got this relation now. V4 by V3 is equal to how much we got? V1 by V2 relation we got. This we will substitute. This we will take for substitution. Okay. So this we will take for substitution. So this we will take to which place in the sense this place. Okay. So V4 by V3 we got no. Now we have to substitute at this place. Okay. So now net work done is equal to minus nr T2 ln V2 by V1 minus nr T1 ln V4 by V3. How much we got? V4 by V3 got to V1 by V2 we got. That will substitute. Okay. So V1 by V2 will substitute. Okay, we are substituted. Next, we will simplify this minus NR T2 ln V2 by V1. This interchange this because it is V2 by V1, it is also V2 by V1 in the sense simplification will be easy. Then it will become plus NR T1 ln V2 by V1. Okay. Then what is the common thing that we can take out? You see now minus NR we can take it out common. NR we can take common, and ln V2 by V1 also we will take common. Ln V2 by V1 also we have taken common. Then what we will get means T2 minus T1 we will get. Correct? Sir. So this is called what in the sense net work done by the system in the Carnot cycle. So in the Carnot cycle, net work done in the sense minus NR ln V2 by V1 into T2 minus T1. Sir. We got net work done, we got it. Sir. Now, what is the internal energy change of a cycle? For this Carnot cycle, what is the delta U? For this Carnot cycle, we got W we got. What is the delta U? What is the delta U? We'll see. Delta U in the sense, now starting point is at where? It is a starting point. Okay, it is a starting point. At starting point means A. Then this at starting point first step is over, second step over, third step is over, fourth step is over. At the end of fourth step the cycle comes back to state A, isn't it? Point A only. Therefore initial state, initial point, final point, same for cyclic process. For cyclic process in the sense starting at one point, going and again coming back to same point, that is only called a cycle. No. So for a cycle, what is the change in internal energy? That is zero. For a cycle, what is the change in internal energy? In the sense zero, we can say delta U is equal to zero in the sense Q is equal to minus W as per first law of thermodynamics, isn't it? So Q is equal to minus W, we can say. So Q, this W, it is network done, that is a W total, then means Q total. So Q total is equal to minus W total, we can say. Now Q total is equal to how much in the sense? Q total is equal to how much we will see. In the first step, heat is involved. In the first step, heat is involved, that is Q2. Second step, Q is equal to 0. Third step, heat is involved, that is Q1 will take. Fourth step, heat involved is 0. Okay. Now, we will take first step. In the first step, heat involved is Q2. Okay. Second step, Q is equal to 0. Third step, heat involved is Q1. Fourth step, heat involved is 0. Therefore, total amount of heat is how much? Q2 plus Q1. That is total amount of heat. Okay. So, we got total amount of heat. We got total work done. Okay. This is about a Carnot cycle. Then, in this Carnot cycle, we will see what is the efficiency of this cycle. What is the efficiency of this cycle? We will see. Efficiency of the cycle in the sense, efficiency of the cycle we want to see. Okay. So, now we will see efficiency of a cycle. That symbol is heat. Efficiency of the cycle in the sense, which terms and all we have to consider. Which terms in the sense, net work done by the system shall we consider. Now efficiency in the sense, suppose we are taking one vehicle, we are giving petrol, 1 liter petrol we are giving in the sense how much distance it travels, how much distance it covers for 1 liter petrol, that is called the efficiency of the vehicle, isn't it? Like that, in this Carnot cycle, what is the efficiency in the sense, how much petrol we are giving to the Carnot cycle, how much work it is doing. That two terms if we take, we can find efficiency. Sir, what is the meaning of how much petrol we are giving? How much petrol we are giving means what? Heat